All right, so remember that exam one is a week from today. Um, so that would be the 26th. And the topics, I think we'll probably have interpolation on it, which is what we're going to start talking about today. Um, but I'll tell you for sure on Monday. Um, all right, so we have started talking about simple compressible substances, and simple compressible substances. You always have that PVT surface that represents its motion, not its motion, uh, its change from state to state. And it's a surface, which means that if you specify two variables, you get the height of the thing. Okay, so that says that at most you need two properties to specify the entire state. And it turns out that when you're at saturation, which is undergoing a phase change, you only need one property. So let's talk a little bit about phase change. And we're going to do this by looking at a temperature volume diagram. So I'm going to put temperature on the vertical axis, specific volume on the horizontal axis. And here's the vapor dome. And let me actually make a change to this. I'm going to make it lean a little bit. Sorry for making your notes look ugly. But okay, it leans a little to the left, like California. And over here is liquid. In here is a mix of liquid and vapor. And over here is a gas or a vapor. Gases and vapors, by the way, people sometimes make the distinction that a gas is something that it's in its vapor form at standard atmosphere pressure and temperature. And then gas. So gas is something that is a gas at standard conditions. A vapor is something that needs to be hotter or higher pressure to be in a vapor form. But in this class, mathematically, you can just think of them as meaning the same thing. Vapor and gas mean the same thing. And we're going to look at what happens as you increase internal energy in a material. So here's the vapor dome. And if you start out with a liquid and you add internal energy to the liquid, it goes like this. So what that's saying is there's barely any increase in volume as you increase internal energy, but there's a noticeable increase in temperature until you hit that. So what are we talking about? The process, we're starting at a liquid and we're increasing internal energy, moving to the next phase up with more energy. So what phase boundary is this? What's happening? We're talking about boiling, and so it's all liquid. Now at this point, it's all liquid, but it's at the boiling temperature and pressure. So it's about to start turning to vapor. Okay, if it's water, it's turning to steam. And then as you keep adding internal energy, the temperature stops going up. That's what happens. So these lines that I'm drawing, I'm going to do this one and then I'm going to do another one at a higher pressure. But these are constant pressure lines. Okay, so you can think of this as like at regular atmospheric pressure. This is like water in a pan that's going from liquid to steam. Okay. Um, and as you keep increasing internal energy, that temperature stays the same until you've put quite a bit of internal energy into it. And at this point, all of that water is now steam, but it's still at the boiling point. Okay. And now, if you keep adding internal energy, it starts doing this. And now it's no longer at the boiling point. It's at a higher temperature and it's getting more spread out. Okay. Remember that specific volume means for the same amount of material, the volume's getting bigger as that goes up. So we have basically the liquid water is incompressible. No matter what its temperature is, it's basically just the same density. It's the density of water, which is what we're used to. Then it gets to that boiling point, and now the temperature isn't going up as you put more internal energy into it, but the volume is going up a lot because these molecules are separating from each other. Okay. And then once you get past that phase change, then you start getting an increase of temperature again, and the volume keeps going up. This is, so at this point, let me make that arrow a little clearer. At this point here, this is a saturated liquid. At this point here, it's a saturated vapor. In between, it's a mix of saturated liquid and saturated vapor. Yep.
Professor, so basically when it's in the middle of that and we add more energy to the material, is it like a fraction sort of thing?
Yeah, it's a fraction thing. Yeah,
And
exactly.
then at that saturated vapor point, it's just all gas?
Yes, exactly. So saturated liquid, it's all liquid. Saturated vapor, it's all vapor, but it's still at the same temperature and pressure. In between, you have various fractions of liquid and vapor. And then as you get outside of that vapor dome, you have either all liquid or all vapor. Yes.
So I'm just asking to confirm, the y-axis is temperature and
Right.
the x-axis is specific volume, right?
Correct. Yep.
So it gets to a certain temperature and then goes along a horizontal line, which the specific volume is increasing.
That's right.
Then both temperature
Right.
and volume increase.
Right. And so while something's undergoing a phase change with a constant pressure, the temperature does not go up at all. So this is for a low pressure. For a higher pressure, it's the same. It's just up here. So this is for a high pressure.
So that would be like a z-axis, but kind of represented two-dimensionally, like a just the curve inside
The curve, well, so we're just saying, so remember the whole thing is a surface. And if you choose constant pressure, you're basically choosing a slice of that surface, and what you have left is just a two-dimensional line. And so that's what we have here is this two-dimensional line. Okay. And the whole vapor dome is just as a backdrop so you can see where it's liquid, where it's a mix, where it's vapor. So remember that the PVT surface, is a surface. We need to look at it in 3 dimensions, and it's hard to do that on paper. I certainly can't like sketch it or anything. But if you go along the pressure axis and just take slices at various pressures, you would have different, the green here represents different slices at those different pressures. And if you take a slice of a surface, it just becomes a line, like a curve. And so what we have here is 2 different slices at constant pressures. And you see, if you have the higher pressure, you're at this higher curve. If you're at a lower pressure, you're at that lower curve. Okay. And so in both of these, internal energy is increasing as you go from left to right. Okay, well, so there is some energy difference between that saturated liquid dot and the saturated vapor dot. There's, because the way you get from one to the other is by adding internal energy. The energy difference between the saturated liquid and the saturated vapor is called the latent heat. And the reason it's called latent, like why is it latent heat? Like sleeping, like it's like invisible energy. Heat is kind of a bad word. It's really internal energy. It's not heat, but we don't get to name it. It's already named. So how is this energy difference kind of like a hidden energy? It's because it doesn't show up as temperature in the material. Like if you look at this curve, okay, it's the one place on this curve where you can add a ton of energy and the temperature doesn't go up. Okay, so it's the one region in here where you can't detect the internal energy by being given the temperature. It could be anywhere in there. Okay. So it's called latent heat because it's internal energy that's not shown by the temperature. Well, this latent heat, yes.
Is there an example for that? Like anything that I can imagine? Like an example?
Yeah. So let me, before I go into this this next thing, let's actually just look at a table. Okay. These tables are things we're going to use sometimes, although we're starting to get away from it a little bit as you can just find this stuff online. But okay, if you go to click, 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 do 47 clicks and you're into D2L, and we'll go to Thermo. And then in the content of Thermo are tables. And let's go to water saturation. So saturated water indexed by temperature. And so let's say, let's go down to, this is Celsius. So let's go to 100. And you can see that, as you know, water boils at 100 degrees Celsius in standard atmospheric pressure. So then it tells you what the pressure is that corresponds to saturated water at 100. And it's no surprise that it's at 1.01 bar, or 1.01 times 10 to the 5th pascals, standard atmospheric pressure. And there are all these different things, all these different properties you can look up. Since we're looking at saturated water, just giving that one temperature is enough to be given all these different properties. So there's a specific internal energy for saturated vapor, a specific internal energy for saturated liquid, specific volumes for liquid and vapor, enthalpy, entropy, all this stuff we're going to talk about later. But let's look at the difference in internal energy between, so in both of these two cases, we have, whether it's a saturated liquid or a saturated vapor, in both of these cases, the temperature of the water is 100 and the pressure is 1.01 times 10 to the 5th. Okay. But now look at the specific internal energy for liquid here and for vapor here. It's the same temperature and the same pressure, but there's a huge difference in the specific internal energy. So that's just the internal, you can think of that as the internal energy for a kilogram of the material, you know. So we only had 419, I think these are kilojoules, kilojoules of energy for that material when it's water about to start boiling. But by the time the whole thing is boiling, still at that same temperature and pressure, we've multiplied that by 6 or so. Okay. And so all that energy is energy that doesn't show up in the temperature and pressure at all. But when you have water vapor, that's energy that's available for you to use for engineering purposes. Okay, so let's go back to, so now that sort of brings me to, this latent heat is really important for engineering. So latent heat is useful in engineering for 2 reasons. The first one is, as we just saw, it's a lot of energy. And now the second one, why is it, and by the way, we're talking about the phase change from liquid to vapor, okay? There's also a phase change from solid to liquid, okay? But we're not really ever going to discuss that in this class. And I don't have tables of that, so I can't show you the numbers like I just did for liquid to vapor. But the reason we're not going to deal with that is because it's not very useful to engineers, not nearly as useful. And the reason it's not as useful is it's a lot less latent heat going from a solid to a liquid than it is from a liquid to a gas. So this is a lot of energy. The energy you get from phase change solid to liquid, it's just not that much. So we'd rather use the one where we have a lot of energy at our disposal. And then what does it mean to have energy at your disposal? we can extract that energy from a vapor without changing the temperature of the atmosphere, the environment, the surroundings. I'll say surroundings, without changing the temperature of the surroundings. So, okay, let's say that, let me sort of illustrate this. So, for example, let's say that we have our gas that has its saturation temperature for some given pressure. At 80 degrees Celsius. Okay. So if this is our gas, and it's 80 degrees Celsius, we can have our surroundings at, let's say, 79 degrees Celsius. And heat will flow from the gas to the surroundings. Okay? We're extracting that energy. The thing is, if you are not at the saturation point, okay, letting heat transfer from your system to your surroundings would make the temperature go down. So after a small amount of heat transferred, this would get to 79.1 degrees Celsius or whatever. And now heat transfer is really slow. Eventually it would get to 79 degrees Celsius and then all heat transfer would stop. There's no way to extract that energy if your gas temperature is going down as heat transfers. Okay? But if you're doing it during saturation, the temperature doesn't change. Are you with me on that?
What do you mean by saturation?
So if you're at that phase change temperature and pressure in your system and you set this up, okay, now heat is going to transfer from the gas to the surroundings. But this time, the gas temperature is not going to go down, specifically because it's at that saturation point. And so now you can extract all of that huge amount of energy simply through heat without decreasing the temperature of your surroundings. Okay? So can you see how that's a useful thing? Yeah, that's a necessary property for heat engines and for refrigeration systems and everything. That's the thing that we're going to try to take advantage of as often as possible. Okay? So all of these systems we're going to talk about, refrigeration systems, power cycles, they can work without phase change, but you just have a very small amount of energy. So say that, ignore the part that this is the saturation temperature. So now just say that it's a liquid and it's water. It's not at its boiling temperature, and say that we want to extract some energy from it. And the liquid water is at 80 degrees and the surroundings are 79. We can still extract some energy. It just is a very small amount of energy before these temperatures are about the same and heat transfer ceases, But when you're at the saturation point, you can pour out a ton of energy. Okay, so now we're going to get into property tables. And going along with using property tables is linear interpolation. And so property tables are compiled results for individual materials, individual substances that let you take either the two properties that you know, specify two properties if it's not at saturation, or specify one property if you are at saturation, and from that, look up all the other properties that go along with that. Okay, it's very useful. The problem is in a table, all you have is finite values. And generally speaking, the so the temperatures in your table might be 90 degrees, 100 degrees, 110 degrees, but you want 92.5 degrees, and that's not in the table. So how do you get that? And that's what linear interpolation is for. Okay. So property tables are for looking up properties by specifying either two properties if you're not at saturation, or one property if you're at saturation. And before I get going on this, so I'm going to teach you linear interpolation for kind of two reasons. One is it's still used in classes, so you might have to see it again. We're not going to spend a ton of like time and effort on it, but you should know it. The second thing is outside of thermodynamics, it's really the principle for almost all numerical calculations, computer methods. And so it's nice to understand this principle as an engineer, even outside of thermo. But let me tell you that everything that we are going to do with tables, you can get much faster by doing this. Go to irc.wisc.edu/properties. So you're going to want to use this website in this class. And let me just quickly show you how it works. Okay, so I'm going to go down to my bookmarks. No, I don't want to bookmark that. Okay, so here's the website. And let's say we want to look up water properties, and I'm going to use SI units, so international units. And I want to look it up at a temperature of 150 degrees Celsius and a pressure in kilopascals of 120. So that is, it says that it's a superheated gas. So that's above the point where all of the water would turn to vapor from liquid. And it has to have this specific enthalpy, this specific internal entropy, also specific entropy there. And so you can look up all this stuff for it. Okay. And interpolation is just used with tables to get a slightly worse approximation of the same information. Okay. One thing I want to show you too while we're here is this makes you specify two properties. So I chose temperature and pressure. You could choose any two properties you want. What about at saturation? So what about if you're talking about what if you're talking about at the boiling point and you have like half liquid and half gas? How would you look that up? Then for your second property, you choose this thing called quality. And quality is, it tells you how much of your saturated mixture by mass is vapor. Okay. You can think of, so why would they call that quality? Again, for the purposes of engineering, it's a very high quality thing if you have something at its saturation temperature, but it's all vapor because it's ready for you to take all this energy out of it. Okay, so you can sort of make sense of it that way. So if I make my second property quality and I say, okay, I want it to be all vapor, that's a quality of 1. 0 to 1, yep, exactly. So if you put 0, so I put in 1, and what we have is a saturated vapor. If I put in 0, all this would be a saturated liquid. And you can see, if you look at that internal energy, it's about what we saw before. Oh, this temperature. Here, let me go down to standard atmospheric pressures where the saturation temperature is 100. This is what it gave us before for the specific internal energy. If I make the quality equal to 0, it goes down to 400 or whatever, 419. And if you want to see what these values are for 60% vapor and 40% liquid, put 0.6 in there, and all these values just change for you. But now we're going to spend a day or two figuring out how to basically do that from, just from tables that you can hold in your hands. Okay. Anyone have any questions about this fluid property calculator? That's the way to go. That's luxury.
So it's the quality is the amount of like.
Yeah, I'll talk. I will reintroduce that in your notes. But yeah, it's telling you the fraction of your saturated mixture that is by mass, your fraction by mass that is vapor.
So are these properties like purely mathematically calculated?
Yes.
And like there was initial testings for certain temperatures and extract from that, or just all?
No, it's all done from first principles of physics, and we just won't get into all of, but it gets very complicated. Yeah, it comes from thermodynamics 3 or something, like then you'd get the equations where you could do that, and it still would be a super tedious job, We'll see some of it, but not enough to recreate whole tables. Any other questions? Okay, so this replaces tables. Okay, so now that you know that tables are useless, let's talk about them. There are 3 types of tables. Saturation tables, like the one I looked at a few minutes ago. And the key thing there is at saturation, one property is enough to look up the rest. And the saturation tables come in two varieties. The first one is indexed by temperature. And the second one is indexed by pressure. They could also make ones that are indexed by specific internal energy, specific entropy, specific enthalpy, any of those, but they don't. They just make these two. Okay. Um, and then the second type of table is a compressed liquid table. And so for these, you need two properties to look up the others. And the way these tables, so how do you look up two-dimensional information in a table? It's separated into sections by pressure. And then inside that section, it's indexed by temperature. And then the third one is, so a compressed liquid is the term for liquid that is not saturated liquid. Okay, so like for example, at standard atmospheric pressure, water at 50 degrees Celsius is compressed liquid. Okay, and then the third one is superheated vapor. And again, you need two properties because it's not at saturation to look up the others. And it works like the compressed liquid table. Table. Um, and let me define quality. So for substances at saturation, we have this thing called quality. So you always, for things at saturation, you have part saturated liquid and part saturated vapor. it could be 100 and 0, could be 100% and 0% could be the parts, but and the quality that we are going to always denote with an X is the mass of the vapor divided by the total mass. So that means that X equals 1 is all saturated vapor. X equals 0 is all saturated liquid. And anything between 0 and 1 just tells you the fractions of the two of them. And here is the reason that quality is useful. For any property Q, so I'm just making up a property called Q that can stand in for anything else. The Q of the mixture is the quality times what Q would be for the vapor plus the quantity 1 minus X times Q, what it would be for the liquid. Okay, let's do just a quick quality calculation. So let's say we have water at saturation at 1.01 times 10 to the 5th pascals. And the quality is equal to 0.8. So the vast majority of it is saturated vapor. What is the specific internal energy? Okay, so you would go to the water saturation table. That's indexed by pressure. You would scroll along until, you would look at the row that says the pressure is 1.01 bar. And you would read that the specific internal energy for the vapor is 2506 times 10 to the third joules per kilogram. This is what you would read. And you would read that specific internal energy for the liquid is 419 times 10 to the third joules per kilogram. And then you would say the specific internal energy of the mix is 0.8 times 2506 times 10 to the third plus 1 minus 0.8 is 0.2 times 419 times 10 to the third. And your mixture would have specific internal energy of 2088.6 times 10 to the third joules per kilogram. You also can use that equation backwards. If you happen to know that your mixture has a specific internal energy of 2656 times 10 to the third, say, you can plug it into this equation where you know these two values. The unknown this time is x, and just solve for that quality. And we'll use that not like later on in the class. That'll be really important to us. Okay, any questions about that? All right, that's it for today.